Welcome back. Today we're going to be talking about skeletal muscle physiology. And this is actually the second video in the skeletal muscle series. If you haven't watched skeletal muscle anatomy, please go back and watch that video first and then come back here. So last time we were talking about the sarcomere, and we were talking about how the sarcomere is the unit of contraction in a muscle fiber. And a sarcomere goes from Z-line to Z-line, and it's composed of overlapping thin and thick filaments. The thin ones are actin, and the thick ones are myosin. And if you will, go ahead and take your hands and put them like this. And imagine your thumbs are the Z-lines. So from thumb to thumb is a sarcomere. As contraction happens, actin and myosin slide past each other and take up all that empty space that was in between them. And as you do this with me, I hope you're doing it with me, you'll see that your thumbs are actually getting closer together. The Z lines are getting closer together, which means the sarcomere is shortening. When muscle contraction stops and relaxation happens, these guys will slide back past each other again, and the sarcomere will lengthen again. So anytime a muscle contracts, the sarcomere gets shorter. And you'll also notice that these myofilaments, actin and myosin, don't have to get shorter and longer. They can stay the same length as they slide past each other. This is called the sliding filament model of muscle contraction. And we looked at this last time. We talked a lot about how there was a darker area in the middle and then lighter areas at the sides, which gave you those muscle striations that you get in skeletal muscle. But let's look a little bit more closely at actin and myosin, because I promised you a love story, and myosin definitely loves actin. In fact, myosin loves actin so much that whenever it can, it's going to grab onto actin because she's pretty and she's fun and she's really cool to be with. And it's going to grab onto actin and pull her. And that's going to cause these sliding filaments to go past each other. Myosin, that thick filament myosin is actually made up of a lot of filaments that are kind of wound around each other. So they make kind of like a big rope. And the ends of each of the filaments has this head. And this head likes to bind to actin. I'm going to use my computer cord. So if this is the head of myosin and this is my actin, it's going to grab on and pull it, and then grab on and pull it again, and grab on. I can't pull anymore because my monitor will fall over, but you get the idea. The problem with this situation is that myosin likes actin so much, it will always grab on and pull, and it will always try to do muscle contraction. But we don't always want muscle contraction. So we have to make sure that this interaction is very carefully controlled. So let's take a closer look at actin. You can see actin is here in red. And the binding sites, those myosin binding sites on actin, are blocked. So when the muscle is relaxed, when that muscle fiber is not contracting, myosin cannot bind to actin because the binding sites are blocked, and they're blocked by something called tropomyosin. So tropomyosin blocks those myosin binding sites. But this isn't good either. It prevents muscle contraction, which sometimes we want, but sometimes we actually want muscle contraction. So we need a protein that's going to move tropomyosin out of the way. And that protein is called troponin. Troponin is going to bind to calcium. So do you remember how we talked about calcium in the last video? Calcium is really, really important. Do you remember where calcium is stored? Calcium is stored in the cytoplasmic reticulum. When calcium is released by the SR, it's going to bind to troponin. It causes troponin to change its shape, kind of pull back a little bit. Troponin is attached to tropomyosin. When troponin pulls back, it pulls tropomyosin out of the way. When tropomyosin is out of the way, myosin can bind to actin. Okay, so imagine here's tropomyosin. This is blocking the myosin binding sites on my computer cord, which is, for today, actin. My hand is going to be the myosin head. It can't get in here because tropomyosin is blocking me grabbing onto the computer cord. But if calcium is released, calcium is going to bind to troponin, and troponin will pull tropomyosin out of the way. Shh. Now the myosin head is free to grab on to actin and start pulling. Contraction will happen. So the big question now is, what causes calcium to be released? Well, for that we have to go to another picture from your textbook. So this is a picture of what happens at the neuromuscular junction. So neuro means the nervous system. Muscular means the muscle. And junction is where the nervous system and muscular system meet. So the axon terminal of the neuron is going to come down and it's going to release a neurotransmitter. The neurotransmitter is called acetylcholine. Now, acetylcholine is sometimes abbreviated as ACH, and it's just a neurotransmitter, which means it's a chemical that's released by the nervous system that's going to stimulate something. And in this case, acetylcholine is going to stimulate muscle contraction. Now, where the neuron meets the muscle, there's something called a synapse. So this is the neuron, and each of my fingers maybe can be muscle fibers, and each one of them is going to come close, but they're not actually going to touch. Do you see how there's a little space between them? So the name of that space is called the synapse, or the synaptic cleft. So it's a little teeny space. So because the neuron doesn't actually touch the muscle fiber, we have to have a chemical that can diffuse from the neuron to the muscle fiber. And you can see that happening right here. Right in here, that's the synapse. So what happens is, in your brain, you decide to move a muscle. It will send what we call an action potential down the neuron. It will cause the release of the neurotransmitter acetylcholine into the synapse. The acetylcholine will diffuse across the synapse and it will bind to receptors on the motor end plate, on the muscle fiber. And that will cause an action potential to travel along the sarcolemma. And remember, the sarcolemma is the plasma membrane of the muscle fiber. The action potential will travel along the sarcolemma until it reaches a T-tubule. The action potential will travel down the T-tubule deep into the muscle fiber. And that action potential is going to trigger the release of calcium from the sarcoplasmic reticulum. Once calcium is released, calcium is going to bind to troponin, which is going to change shape, and then it's going to pull tropomyosin off of those binding sites. Finally, myosin is going to bind to actin and cause shortening of the sarcomeres. That's skeletal muscle contraction in a nutshell. See you in class.